So let me just make sure that I'm actually recording. I don't see the, yeah, I think we are recording. Okay, so once again, the set of all physical transformations on a given set of objects that leave some property of those objects unchanged naturally form a group. And the transformation that is the null transformation that doesn't do anything to the objects is the identity. If you can make one transformation, you can normally invert that transformation. So that's the inverse. Transformations are naturally associative. And if one transformation leaves the property unchanged and another transformation leaves the property unchanged, then if you follow one with the other, the property is automatically unchanged. So that's the really important thing. And last time we reviewed a variety of classes of groups. The one that was puzzling, not only to you, but perhaps, but also to me, is this symplectic group that's very rarely talked about in physics courses. Even though I think it's going to be important someday, and it's obviously important in that it's the set of real matrices that leave invariant the commutation relations of quantum mechanics. So, I mean, that's bound to be important. And in fact, what's an example of such a transformation? Well, suppose these quantum mechanical variables, NQs and NPs, evolve forward in time, then the transformation that makes that happen is the time evolution operator, and that's got to be a member of the symplectic group because it has to preserve the commutation relations. There's a similar theorem in classical mechanics, which says that if the, I forget exactly what it is, but basically if the evolution of these variables Q and P preserves the, I guess the Poisson brackets, then the evolution is Hamiltonian. I'm quoting that from my head though, rather than reading it. So so don't bank on that. You can flip ahead to the section on the permutation group for more information there. Let's though first look at an example, the simplest example of the permutation group is sp2r. So these are 2x2 real matrices that preserve the commutation relations of Q and P. I decided to call these matrices T because we already have R standing for real. So Q prime and P prime are related to Q and P by an arbitrary real matrix ABCD. And so we have if we want to preserve the commutation relations, well, the only one that we have is we want Q prime, the commutator of Q prime with P prime to be IH bar. So that's AQ plus BP, commutator CQ plus DP. Now that automatically by the commutation relations is IH bar AD minus IH bar BC. And we want that to be IH bar, so that just means that AD minus BC, which is the determinant of the matrix T, has to be 1. Incidentally, that means that sp2r is the same group as SL2r, which is real linear 2x2 matrices that have determinant 1. It turns out, and you can verify this by looking in the section on the symplectic group later on in chapter 11, that the 2n by 2n matrix T has n times 2n plus 1 arbitrary real elements. So it's obviously non-compact. By the way, I put chapter 11 on group theory. It's on the class webpage. And there's a link to the class webpage on the physics department webpage under classes. All right, so let's see. By the way, the more questions you ask, the better class will be. Otherwise, I just ramble on. Anyway, a Lie group is a group whose elements depend continuously on a set of parameters. And in physics, that's what we normally talk about. Well, in some areas of physics. In other areas of physics, in solid state physics, we're sometimes concerned with crystal groups of crystals. And I suppose they're big in Santa Fe. But anyway, the groups, the orthogonal groups and the unitary groups are continuous Lie groups, and so are the symplectic groups. Now, last time we talked about representations of groups, and the idea here is that you have in the group, you have a multiplication law. F times G is obviously FG. And so if you can find square matrices, D of G, one for each element G of a group G, and the multiplication law of the matrices is the same as the multiplication law of the group elements, then what you have is a representation of the group. So that's a very nice and natural statement. The reason why we use capital D is, I think the German word for representation, I think, is something like Darstellung. And so you see what happens when you don't have leadership in science. The language changes, and when you regain the leadership, you're saddled with all sorts of Germanisms in this particular case. We may, in another 20 years, be saddled with various Chinese terms. Because after all, we have the best Congress money can buy, and it hasn't invested in science properly for 50 years. Anyway, examples of representations are the rotation group in 2 and 3 dimensions. One thing which we don't need to dwell on, but I'll just mention, is that compact groups possess finite dimensional unitary representations, but non-compact groups do not. And so you might say, well, wait a minute now, the Lorentz group is non-compact, and we represent it by unitary transformations, and unitary transformations are compact in some sense because U adjoint U is the unit matrix or unit operator. Well, the point is that that's an infinite dimensional representation of the Lorentz group. Here we're talking about finite dimensional representation. So non-compact groups can have infinite dimensional unitary representations, but not finite dimensional unitary representations. Let's go on. If you have a matrix like this, it's said to be in, well, first of all, what's an equivalent representation? Anytime you have a representation, you have infinitely many equivalent representations because you just perform this operation with any matrix DS, any matrix S that has an inverse, and you get another representation that's just as good. Might even be better. And because D of G is a representation, D prime of G will also be a representation because of this equation. Now, in particular, you can sometimes take a representation and find an S that casts it into block diagonal form. In that case, you say the representation is completely reducible. And by completely reducible, we mean it's not only in block diagonal form, but these individual representations, D1 and D2, are themselves irreducible. The state, the vector space that D1 acts on is, of course, a subspace of the whole vector space because it's just the top corner. And the same thing for D2 and D3. And so that shows you that if a representation has a proper, and of course, D1 maps vectors in that subspace into the same subspace because this is a square matrix. So a representation that has a proper invariant subspace is reducible. Anyway, when you have this situation, namely that a representation can be written in block diagonal form, then what we say is that it's a direct sum of various irreducible representations. Now, in quantum theory, a symmetry transformation, as you know, is a map of states, psi to psi prime, phi to phi prime, such that the inner products have absolute values that are equal. And so that's what we mean by a symmetry transformation. Now, long ago, back in, I think, the 1930s, while he was still in Germany, Wigner showed that symmetries in quantum mechanics can be represented either by unitary operators, that is to say, operators that are linear and unitary, or spooky operators that are antilinear and anti-unitary. And the English translation is a book, Group Theory and the Quantum Mechanics of Atomic Spectra, which was the English translation was published in, I guess, 59, and maybe depending on which edition it was published in 64, apparently, as well. Weinberg put some finishing touches on that, and that's in volume 1 of his 3-volume treatise on quantum field theory. Now, I don't know how much of this to go through in enormous detail because I don't know what the students want, or I should say the student and the colleague want me to go through. This is just a definition, namely 2 operators that commute are said to be compatible, and a set of compatible operators is complete if you could use those physical properties to distinguish every physical state from every other physical state. So to every set of eigenvalues, it's complete if to every set of eigenvalues for the whole set of operators, F1, F2 up to Fn, there's only a single eigenvector. So the state that has given values for the eigenvalue of F1, F2, ... Fn, the state that has all those eigenvalues, there's only one state that has them. And if you change one of them, you switch to another state. We went through last time, and I think maybe I'll just state the result and you can look through it in more detail yourselves. Suppose you have a Hamiltonian that's typical Hamiltonian, and it's invariant under the square of the rotation operator. It's rotationally invariant, so it's invariant under JC and also under J squared. And suppose these form a complete set of compatible observables, and that, for example, was what we thought was true of the hydrogen atom before the Stern-Gerlach experiment uncovered spin. Anyway, the identity operator then is the sum of outer products, and the matrix element of a unitary operator between two states then has this form. And if we go through a little bit further, what you find out is that this unitary operator, which is representing basically a rotation, it will have matrix elements that look like are of this form, and we're summing here over E, J, M prime, and M. At least that's the way it would be initially. We can actually simplify this further, and I'll show you a little bit later here. Subgroups now, if all the elements of a group S are also elements of a group G, then S is a subgroup of G. And of course, there are always two trivial subgroups, the identity element and the whole group G. On the other hand, groups can have more interesting subgroups. The rotations in 3 space have as a subgroups the rotations about any given axis. A subgroup is an invariant subgroup if for every S in that invariant subgroup, the action G, S, G inverse gives you S prime, another element of the subgroup. And that subgroup is said to be invariant under the action of the whole group. You can write it this way. Invariant subgroups are sometimes called normal subgroups. I think I'm going to skip conjugate class and center, but it's here in the PDF that's on the class webpage. I'm also going to skip cosets. It's amusing, but it's more pure mathematics than physics. Let me come to Schur's lemma, and of course, you can be sure of Schur's lemma. So suppose D1 and D2 are 2 inequivalent, irreducible representations of a group G. And also suppose D1G times some matrix A is equal to A D2 of G for all elements of the group. Then what Schur showed was that A had to vanish. We can go through the proof if you want, but I think it's probably better for me to let you read the proof. Let me go to now to part 2. Part 2 is if for a finite dimensional irreducible representation D of G of a group G, we have D of G A is equal to A D of G's of some matrix A and all G in G, then A is a matrix, a multiple of the identity. That is to say, any element, any matrix that commutes with every element of a finite dimensional irreducible representation must be a multiple of the identity matrix. And so once again, I'm going to skip the proof and just go to the example. So suppose we have an observable that's invariant under some unitary operator U of G. And suppose that these commute with J squared and with H. In other words, they're rotation operators. And so then if we go back to this example where we were, here, let me just jump back to it for a second. We got down to this equation here. So if we go forward now and see what this actually means here, let me make this bigger so that it's easier to see. So what do we have? So let's go back to the previous relation. We found then that we had this particular equation, or more especially using the notation that we adopted before, we have this expression here. But now this is an irreducible representation of the rotation group. Or if it were some other group, not the rotations, but something else, it would still be an irreducible representation. So part one of Schur's lemma tells us that this matrix here, which is commuting with D, must vanish unless the representations are equivalent. So that means that these two representations are equivalent, but that means that J prime is equal to J. So now we get down to this point. But then part two of Schur's lemma, well, what do we have here? First of all, we have an irreducible representation. We have a matrix that commutes with the irreducible representation. Well, part two of Schur's lemma tells us that that has to be a multiple of the identity. And so it has to be diagonal in J and M like that. And this OJ is just a number. So this is a special case of the Wigner-Eckhart theorem. And what we see here then is the Wigner-Eckhart theorem is a natural consequence of Schur's lemma. Characters are something that's amusing, but I think I'm also going to skip that. Suppose we go to direct products then. Now, this is something that occurs all the time in physics, because in physics, we often deal with composite systems. And so that means that we have some transformation that acts on two different systems described by states labeled by an index M and an index L. Or actually an index J and an index L. And so the action then of the transformation, typically a unitary transformation on the composite system, is then going to be a product of these two, this representing how the transformation acts on one part and this how it acts on the second part. And so the states of the composite system then have two labels. So the transformation acting on the composite system states is then decomposed into one representation acting on the first system and the second matrix acting on the second system. And so that's how that works. The example that you see in quantum mechanics is the addition of angular momenta. And so suppose we have two systems, one of angular momentum J1, the other one of angular momentum J2. Then the composite system has representations that are bigger systems, namely they are 2J1 plus 1 times 2J2 plus 2, 2J2 plus 1 dimensional square matrices. So they're huge, but they're reducible typically. And a theorem that we're not going to go through, but for SU2, which is what, or SO3, which is the rotation group, this composite representation D of J1, J1 plus J2, or J1, J2, is a direct sum of all these irreducible representations from D of J1 plus J2 down to G of J1 minus J2 in absolute value. Let's do an example here. Suppose you have two spin 1/2s, then the composite rotation then is equivalent to of course this one will be 2 by 2, this will be 2 by 2, so this is 4 by 4, but it's equivalent to a 3-dimensional representation and a 1-dimensional representation. And so that's your standard thing in quantum mechanics, namely that, let me see if I can make a new note here. In other words, and let's see, I wanted to have that note appear somewhere, and I don't see it appearing here. All right, I don't know where it went. Maybe I'll just start this over again. Okay, so let's see. Now I forgot what it is that I wanted to write, but in general, if you have a system J1, J2, then in other words, two rotations acting on two systems, one with angular momentum J1, one with angular momentum J2, then the total representation is, it'll look like this. And this one here will be one that is for J1 plus J2. So this will be 2 J1 plus J2 plus 1-dimensional square matrix. Then there'll be one here that'll be 2 J1 plus J2 square, and then dot, dot, dot down to 1. That's the absolute value of J1 minus J2 times 2 plus 1 dimensional square matrix. So that's the way it works. This was the case of adding 1/2 plus 1/2. If we imagine adding 1 and 1, then what we would get would be a spin 2, which would be a 5 by 5 matrix. And then we would have spin 1, which would be 3 by 3. And then we would have just a scalar. And so this would be equal to some D2 plus D1 plus D0. And I hope the dimensions add up correctly. Finite groups are of interest to people studying crystals. I'm gonna skip that, but you can certainly read it. It's right here, and if you have a question, you could send me a question and I'll puzzle over it and get back to you. Permutations are intuitively obvious because we all know what it's like to line up for something, and we also know what it's like for somebody to jump the line and go from place N to place 3 or 2 or even 1. So we have an intuitive understanding. The difficulty of understanding permutations is only one difficulty, and it's the notation. The notation can be confusing, and there are probably several different notations, and I'll just leave it at that. And I've already talked about compact and non-compact groups, the translations, the are non-compact. Lorentz transformations are non-compact. General coordinate transformations are non-compact. On the other hand, rotations are compact. Symplectic transformations are non-compact, but rotations and what I meant was the orthogonal groups and the unitary groups, of course, are compact. All right, now here's the really important insight that was made by Lee a long time ago. And as often happens when some great scientist is dealing with a problem, the important contribution of the scientist is, the most important contribution is often not what he was trying to show, but rather the techniques he developed in order to show what it is that he was trying to show. And so in the case of Lee, Lee was studying differential equations in, I think he was actually doing differential equations on curved manifolds and so forth. And these were really quite hard problems. And what he developed was continuous groups and the theory of Lie algebras. So let me take you through that. First of all, we've seen these continuous groups that they depend upon continuous parameters, and they can be quite complicated. What's much simpler is the structure of the group near the identity, and in particular, what's called the Lie algebra. And so what you do is imagine that D of alpha is an n by n matrix that depends upon a certain number of parameters, alpha. And so you take the derivative, the partial derivative of the matrix with respect to each of the parameters. And then because we're in a physics department and we have a fetish or compulsion of using Hermitian quantities, we multiply by minus I to make the thing Hermitian. In that case, the matrix near the identity is the identity matrix plus I times the parameters alpha sub A, TA, and we sum over A. TA then is called the generator of the representation. And of course, this, if we replace alpha by alpha over n and let n go to infinity, then what we get here is this expression, and this is exact in the limit of large n. And then the nature of the exponential is such that if we take the limit, n goes to infinity, of this expression raised to the nth power, we of course get the exponential e to the I, the sum of alpha sub A, T sub A. And we call that D of alpha then. And then moving backwards, we can see if this is D of alpha and we take the minus I times the partial of D with respect to alpha sub A, at alpha equal to 0, we get T sub A, okay? So all these I's are just to make the T's Hermitian. And the result is that the D's are unitary. And of course, what mathematicians do is they just make the generators anti-Hermitian, and then the D's are automatically unitary. Anyway, D inverse has a minus I here, and that's the same thing as D adjoint, because D adjoint would just adjoint all this. This is Hermitian, and so you get a minus sign there. So once again, compact groups are finite dimensional unitary representations with Hermitian generators. So those are the things that are important in many areas of physics. Now, what's very nice about Lie algebra. The Lie algebra of a given Lie group, what we'll see is very nice about it is that the algebra is the same. It's a property of the group. You have the same algebra no matter what the representation is of the group. And so let's see how this comes about. Suppose d of alpha is e to the I epsilon ta. No sum, just one generator. And d beta is just, well, I should have had a beta there, shouldn't I have? Yes. Well, all right, I was thinking of it infinitesimal. Anyway, suppose d of beta is e to the I epsilon tb. So in other words, the alphas are just epsilon for only the case I equal to A, and the betas are epsilon, but only for I equal to B. Okay. The inverses of these group elements obviously look like that, and they're represented by these matrices. And so now if we take this multiplication law, which is we do the G of minus alpha, minus beta, alpha, beta, then that is some other group element, and gamma is whatever the group is, whatever the parameters are of that group element. And so the matrices of any two representations with generators, D with generators TA, D prime with generators TA prime, they have to obey the same multiplication law, the multiplication law of the group. And the point, what's the same is the coordinates here. And so what do we have? Well, and since these are all infinitesimal, we can approximate the product like this. And it turns out that this product here is just 1 plus epsilon squared times the commutator. If you do it in the other representation, which is this, you get the same thing just with primes, and so you have 1 plus epsilon squared times the commutator of TA prime with TB prime. So now these products both represent the same group element, gamma of alpha and beta. So they have the same infinitesimal parameters, and therefore are exponentials of the same linear combination of generators. In this case, we'll call them TC. The same combination of generators. And so the generators in the case of the unprimed representation are just the TCs. And so we have that 1 plus epsilon squared, the commutator of TA with TB is 1 plus. And now what would this be? Well, the generators here, and that would, and we're going to call them, well, it's just some arbitrary linear combination of the generators, but it has to be the same arbitrary linear combination of the generators because it's representing the same gamma here. And so what that means then is that these coefficients have to be the same. In other words, the commutator of TA with TB in the unprimed representation, if that gives you I, FCA, BTC, then the commutator of T prime A with T prime B has to be the sum of I, the same structure constants times TC prime, or T prime C. So that, the point here then is that, well, first of all, these F's are called structure constants. And so the bottom line then is that the commutator of any two generators is a linear combination of the generators. That's the first fact. And the second fact is that the coefficients of the commutators are the structure constants of the group, and they're the same for all representations of the group. So that's the very nice thing about Lie algebras, namely that you have a Lie group, and if you look at the actual matrices that depend on some 20 or 30 or 5 or 10 or 3 or 4 continuous parameters, these are bewilderingly complicated. On the other hand, the group is also characterized completely by its structure constants, and that's just a finite set of numbers. And and they're the same for all representations of the group. And in fact, there are, not only do you have infinitely many equivalent representations for any given representation, but you have, for most groups, infinitely many inequivalent representations. In other words, bigger and bigger representations. For example, the rotation group SO3, you have a 3-dimensional representation, you have a 5-dimensional representation for spin 2, and then I guess it's a 7-dimension or whatever for spin 3 and so forth. Actually, it's probably not 7, but anyway. So this is an enormous simplification, and of the many things that Sophus Lie was investigating in his papers and books, the most complicated ones are very special, and we don't use them all that much. But these things that he discovered are much simpler and very general, and consequently, they're very important. So this is very important. Now, unless the parameters are redundant, and of course, we would not want to have redundant parameters, that would be just stupid. The generators are linearly independent, and they span a vector space. Remember, a vector space is just a set of things that can be added together and can be multiplied by numbers. And so these are matrices, obviously. They can be added together, multiplied by numbers, so they form a vector space. Any linear combination can be called a generator. And then when you have a vector space, you always can make you can find the linearly independent vectors. You can make them orthogonal by one procedure or another. The standard procedure is the Gram-Schmidt procedure. And so you say, well, the inner product of two generators, we're going to define it to be the trace of T adjoint TB. And on the other hand, these T's, if these T's are Hermitian, then this is just TATB. In any case, we can make them orthogonal. And so then we have some K, which is non-negative because this is intrinsically positive when A equals B. And so this is K delta AB. So this is the normalization that we normally impose for convenience. Otherwise, you don't know what you're doing. You can't set K equal to 1. You might be tempted to, but in fact you can't, because we want the structure constants to be the same for all representations. And for that reason, the generators don't wind up with the same norms. So the thing that has to be the same for all representations is the multiplication law, because they're all representations of the same group. And that means the structure constants have to be the same. But once you've got that, you can't get the normalization the same. Now, I'm going to be using the summation convention. So instead of having these sum symbols, I'm just going to write them like this. And so we sum over repeated indices. Now, a few manipulations can tell us a lot about these structure constants. In particular, suppose you multiply both sides by TD dagger. And so we multiply, we take this thing and multiply by TD dagger, and then we get this expression. This, on the other hand, is that, and so we have this. But on the other hand, the Gram-Schmidt process has given, or some other process has given us that this trace is just K delta CD. And so carrying out the sum over C, we find that we get that this trace is IKFD And so this is a formula for the structure constant, namely FCAB is minus I over K, K being a normalization constant for each representation of each group. And they're usually very simple numbers, similar to 1, √2, things like that. It's the trace of the commutator of A with B with the adjoint of TC. You may be wondering, why do I thought we had all those I's in order to make the T's Hermitian. Well, that's true, but we can only make the T's Hermitian if the groups are compact. So if we want to be general and consider representations of non-compact groups, then we have to consider that the T's, the generators, are not Hermitian necessarily. Because now this commutator is obviously anti-symmetric in A and B, because of course TA TB is just TA times TB minus TB TA, and so obviously this is equal to minus TB TA. So this is anti-symmetric in A and B. So these structure constants are anti-symmetric in their lower indices because the commutator is anti-symmetric. Now, you can always, if you have any matrix A, you can always make a Hermitian term and an anti-Hermitian term. And so you can separate the generators into ones that are Hermitian and ones that are not Hermitian. And the exponential of any imaginary linear combination of Hermitian generators is a unitary matrix. On the other hand, the exponential of an imaginary linear combination of anti-Hermitian generators is a real exponential, and the squared norm can grow or shrink without limit as the parameters go to infinity. So these are the non-compact these are the non-compact representations of the non-compact groups. Non-compact finite dimensional representations of the non-compact groups. Now let's see that the compact groups have Hermitian generators. Well, they do. We just saw that, because if the thing is Hermitian, then if the generator is Hermitian, then the representation is unitary, and if the representation is unitary, then the group has to be compact and so forth. So for compact Lie groups, we have Hermitian generators. And so the structure constant formula becomes simpler. We can replace T dagger with T. We have this. And then we have the property that the trace is cyclic. What that means is that the trace of AB is equal to the trace of BA. And the reason for that is that this is equal to a sum of AIK BKI, and this is the sum of B, let us say KI AIK, and so these are obviously equal. So that means that you can always say trace ABC is equal to trace CAB is equal to trace, now let me do this correctly, well, no, I did ABC, so let's go the other way. So this is BCA. Okay, so those are the three, that's the cyclicity of the trace. By the way, normally when I say something about mathematics or physics, I'm right, but when I spell a word, don't bank on the spelling being correct. I'm not a great speller. Okay, so let's go through this. For a compact Lie group with Hermitian generators, what do we have? We just have that the formula then for the structure constants looks like this. We can rewrite this commutator. We can expand, and we get this. Then, on the other hand, the cyclicity of the trace allows us to move this one, to move this guy here, we get this. And then to move this guy to the end, we get that. And now we say this is the commutator of TB with TA. So this is FCBA. On the other hand, we're anti-symmetric in the lower indices, so this is minus CAB. And so now we've got that you interchange A and B, you get this relation. Interchange B and C, you get that relation. And the upshot is that the structure constants of a compact Lie group are totally anti-symmetric. So we have all of these relations. And what people normally do, or sometimes do, is they just drop the index C and put it here or there. And in either case, you've got, well, these two are equal, because if you go to the right, you get a minus sign, another minus sign, so you get a plus sign. So that's just an easier way of writing. On the other hand, if the group is non-compact, you don't have this total anti-symmetry, and so people often leave one index up. So what we've learned here is that for compact Lie groups, the generators are Hermitian. Structure constants are real. Why are they real? Well, the complex conjugate of this trace formula, if you take the complex conjugate, you get a plus I here, and then you get the order switched around. In other words, TC, TB, TA, but all with adjoints, but they're all Hermitian, so the adjoint goes away. And then you can move TC to the end without any problem, but if you interchange B with A, you get a minus sign, but this is the formula for FABC. And so indeed, the structure constants are real. So for compact Lie groups, you have structure constants that are totally anti-symmetric, the same for all representations, and real. The structure constants are real. And the commutator of any two generators is a linear combination. So it's an imaginary linear combination of the Hermitian generators. And the FABC are, as I said, totally anti-symmetric for compact Lie groups. So let's see, I've been rambling on for about an hour, and I haven't heard any questions. I'm going to get some water. Why don't you guys think of a question and ask it? Hearing no question, let me say something about Yang-Mills symmetry. This actually is easy to understand when explained correctly, and I hope I've explained it here correctly. So of course, we're talking about a field theory, like, for example, Maxwell's electrodynamics or some quantum field theory. And what Yang and Mills did was they showed that you could have a field theory whose action is unchanged when a space-time dependent unitary matrix maps a vector of matter fields into another vector of matter fields. Now, for things like psi dagger psi is a vector of matter fields. In other words, what we're talking about here is psi might equal, for example, neutrino electron, or psi might equal up quark red, up quark green, up quark blue. So that's what we're talking about. And so psi dagger psi is invariant because under a unitary transformation, because you would have psi prime would be u psi prime dagger would be psi dagger u dagger. And putting the two of them together, you just see the u dagger u. Well, that's unitary, so this gives you the identity. So that was clear that you could do this. What wasn't clear was how you would get kinetic terms in the action to be made invariant, to become invariant. And what Yang and Mills did was they introduced matrices of gauge fields and replaced ordinary derivatives by covariant derivatives. So wherever they saw an ordinary derivative on psi, so in other words, they changed di psi went to di psi, which is di plus ai psi. And so, and why did they do that? Well, they did that because they wanted di plus ai prime on u psi to equal u di plus ai on psi. So in other words, just as the field transforms from psi to u psi, they want the covariant derivative to be such that the new covariant derivative is just u times the old covariant derivative. In other words, the covariant derivatives transform just like the vectors transform. And so they basically wrote down this equation and they matched this with that. And if you just multiply this out, what do you get? Well, you get diu times psi, I'm just multiplying this out, plus u di psi plus a prime I u psi. That's all there is on the left-hand side. So let me just get rid of those two. And we want that to equal u di psi plus u ai psi. Okay, so we can cancel these two guys. And then we can say, well, we want this equation to work. Well, this equation will work if di, that's not a very pretty di, let me do a nicer di. Di, the partial derivative of u plus ai prime u is equal to u ai. Well, that means that ai prime u is equal to u ai minus diu, or ai prime is equal to u ai u adjoint minus diu u adjoint. So this is the transformation law of a Yang-Mills theory. And that's what they figured out.
Can I ask a question here?
Sure.
Ask a question. Yeah, so whenever you write this expression for the covariant derivative, I often think to the expression for the canonical momentum in electrodynamics. And there you have this extra factor that's like charge that goes in front of A.
Right. That
Vector
plays the role of a coupling constant. Absolutely, yes.
Yeah, and there it's like a U1 gauge symmetry, right? So certainly you have only one generator. So these T's I would think of as like some type of charges. Is this like an interpretation that people actually give whenever they think about like the SU2 gauge theory of this like electroweak theory, or like SU3 for
Right. Well,
quantum chromodynamics.
for the SU2 part, what you have is psi is, for example, nu E. And this is actually just the left-handed part of the field. So let's think of something that's simpler, namely the field for the up quark, say. Well, the field for the up quark would be up red, up green, up blue. So there'd be, because there are three colors for the quarks. And so you would have transformations that would be 3 by 3 matrices acting on these three-dimensional vectors. And the generators would be 3 by 3 matrices. The group is SU3. And this is the theory called quantum chromodynamics. Now, of course, I mentioned this as though this was something that were perfectly clear and simple in my mind and other people's minds, but in fact, it contains a huge puzzle, and the huge puzzle is, why are these quarks confined? And that's something that's really quite hard to explain. But all right, so let's leave aside the confinement issue. But by the way, when Liang and Mills were originally proposing their theory, people didn't want to accept it because they didn't want something like, they didn't want to rotate a neutral field like the neutrino into a charged field like the electron. Here for SU3, it's just different colors. And when Yang and Mills were doing this in the late 50s, these quarks weren't understood. And I think they were thinking about rotations of things like pi mesons. And so they might have been thinking of something like pi plus, pi 0, and pi minus. And people were saying, my God, how are you going to rotate a charged field into a neutral field and so forth? And so there was some resistance to their paper, but but then other people who were also smart, such as Schwinger, for example, Weinberg, Glasgow, and so forth, realized that that this was a very good idea and went on with it. In any event, when you see, I got this transformation law is then this equation 86 here. And notice that in the case, for example, of SU3, these are 3 by 3 matrices, 3 by 3 unitary matrices. And these are 3 gauge fields. No, not 3, they're actually 8, because let's see, what do I want to say? Actually, we have 2 different representations here. You see the quarks transform as here under under the defining representation of SU3, which is 3 by 3. On the other hand, the gauge fields transform according to what's called the adjoint representation. So there are actually 8 of them. They might be 9, but for the group SU3, this requirement that all the determinants be 1 means that the last generator isn't there, and so there are 8 generators, and of course that's why there are 8 gauge fields, because this AI of X is actually a sum of TA AAI of X summed over the A's, and there are 8 generators of SU3.
Yeah, so maybe this is a good place for me to slip my question in again.
Yeah,
Yeah, so certainly for U1, you only have one generator,
right.
right? And there's sort of like one physical quantity that tells you something about you interacting with that one gauge field, right? Which is the electric charge that you have, which
Right.
is it would be like an additional symbol that comes out here, right? But
Yeah.
so can I think of interaction with each of these different gauge fields as being associated with some different physical, like 8 different physical quantities that the particle or whatever I have could possess?
Well, what we have here is a coupling constant G, which measures the strength of the strong
Oh
interaction.
yeah, you did write G, didn't you? Yeah. Oh, okay. So there's really only just one big coupling constant, though.
For each, yeah, for each symmetry, yeah.
I see. I see. I see. So it's not okay. 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 We don't have different coupling constants for each uh
Each
gauge
generator,
field.
no, that would
Yeah.
that'd
I
be
see.
unnecessary. And
I see. I
now,
see.
an important thing that Yang and Mills, which Yang and Mills recognized, was that the commutator of two covariant derivatives, well, if you just multiply it out, you have di plus ai, commutator dk plus ak. Well, the derivatives commute with each other. So all you have is diak minus dkai, and then you have the commutator of these two matrices, and these are matrices because they're linear combinations of generators. And so then you can ask, well, how does this field strength or Faraday tensor transform? Well, we know how these guys transform, namely with a D. So in other words, this F I K is the commutator of DI with DK. And so, whoops, I don't want that. So F prime IK then would be, what did I want to say? U DI, U DK. And what is that? So that's U DI, U DK minus U DK, U DI. And this is going to be nice if we put in here a U inverse. And I think, yes, there is a U inverse naturally here. I didn't write it down originally. All right, so let me show you where that comes from. So we have a U inverse there, a U inverse there. Well, the U inverse U cancels. The U inverse U cancels, and so what you have simply is U FIK U inverse or U adjoint. U inverse. U inverse. Now, where did the U inverse come from? Well, here you see, you have here the D. You want the primed AI to cancel this U, so you have to have a U inverse there. So let me go back to the original equation and see if where well, yeah, the AI prime has a U adjoint on it. See, that's the U inverse. And so the expression for D is DI prime is U DI U inverse or U adjoint. So then the left-hand side of the equation is di prime psi prime which is U di U inverse U psi, is equal to just U di psi, which is what we wanted. So that's it's not the whole story of Yang-Mills theory, but those are the basic that's the basic idea of Yang-Mills theory. And as I said, when they proposed it, people were quite, well, people didn't accept it immediately, and but it wasn't long until, in fact, it was proposed, I think, I don't know what year. It was either the early 50s or the late 50s, and by the late 60s, and in fact, it wasn't even the late 60s. As soon as Yang and Mills proposed it, I think, Schwinger realized that this was probably the way to think about the weak interactions, and that abelian gauge theory should be generalized to non-abelian gauge theory the way Yang and Mills were suggesting it. And in fact, he assigned that as a thesis problem to Glashow. And so Glashow wrote a thesis on it and some other papers on it, and won the Nobel Prize, which he shared with Weinberg, who in the late 60s produced a model of the electroweak interactions that that was realistic because it used the Higgs mechanism to make the gauge fields massive, which was necessary to make the interactions weak. I guess you could have just put in very small coupling constants, but well, I don't want to. That's another law, another path. I don't think I ought to go down that at the moment. So let's see. We're just about out of time. I wish the two people could, Austin and James, could maybe find students who would like to register for this course. Otherwise, it's liable to be canceled. I think the chairman's willing to entertain a course that, or talking the dean into authorizing a course that has 3 students, but I don't think anybody's going to authorize.
I think we have to be registered, right? It's kind of the issue. And I don't really have, I can't register. I mean, because
you're on an RA already.
Yeah, I'm on an RA, so yeah. I'm kind of just a spectator.
Would you do me a favor? Send an email to Rand and Roy, Musumi Roy, you know her, right?
Mm-hmm.
All right. If you could do the department some good by sending an email saying that you would like to register for my course, but you're on an RA, and so you can't without finding a lot of money, or asking your thesis advisor to pony up a lot more money than he or she is already paying you. This is a perennial problem, and it means that we always have trouble in this department finding students for advanced courses unless the course is of enormous interest to a large number of is of interest to a large number of students. And the result is that we very rarely teach the second semester of quantum field theory. We've never had a course in supersymmetry.
Yeah, I think they're struggling with the same problem with this quantum error correction course that one of the new professors at ECE is teaching.
It's just terrible. And if other universities that have large numbers of students, well, or different rules, can teach a whole variety of advanced courses. And the problem is not that we don't have is not that we lack the faculty. The problem is that we lack the mechanism to register the students and have the dean approve the courses. And somehow, I've been mentioning this for decades, and but I've never been, you know, chairman of the department, and no one would ever think of making me chairman of the department. And so I don't know, what I say just gets ignored, and I don't know. But
Well, I'll see what I can do.
yeah, if you send an
and-
email to
Cool.
Rand and Roy and just mention that, and you could also mention that the same problem is occurring for the error correction codes problem course.
Mhm, mhm.
You know, that might
Sure.
make these guys realize that I've been telling the truth for the last 20 years. All right,
Sure.
so this is the end of
All
the
right.
class. Sorry to go on so long about.
Yeah, no worries. I
other
gotta jump
things.
off, but thanks for the
Have a
thanks for the
nice
class.
evening and weekend, and
See ya.
stay healthy.
Yeah, you too.
Okay, bye.
Thanks, Kevin.
Bye, James.